Hello to you all. I would like to start by thanking the SGRT community to give us the opportunity to present what we are doing with SGRT in UZ Leuven on the different radiotherapy modalities. We are part of the health science campus Gasthuisberg in Leuven, which employs over 10,000 people. The radiation oncology department itself treats about 2,800 patients every year. Let me also acknowledge the medical physics team here in front of the first Halcyon in Leuven back in 2017. They have been the driving force behind implementing SGRT in the department and provided most of the material I will be showing you in this presentation. In Leuven we have three Varian TrueBeam systems, two Halcyons and a Proteus 1 from IBA for proton therapy. All of them have been equipped with surface scanning technology, as we strongly believe in the role of SGRT in radiotherapy. The SGRT team consists of an enthusiastic team of RTTs. They have received additional training from medical physics. They are importing the patients in the Align RT system. They're the primary point of contact for other RTTs and train also other RTTs. There's also a medical physics expert group focusing on SGRT. Who look into new indications for setup, new applications of SGRT, and also the periodic quality control. Here you see the recent history of SGRT in UZ Leuven. We started end of 2017, beginning of 2018. Installing the first system on a TrueBeam and started off with deep inspiration breath hold. In the meanwhile, we evolved towards using SGRT for over half of our patient population. Let me give you an overview of the different applications we have of SGRT in UZ Leuven, both in conventional radiotherapy and also in proton therapy. Let me start with conventional radiotherapy on a C-arm linear accelerator, the Varian TrueBeam. We do deep inspiration breath hold for left breast since 2009. We use the Varian RPM system for that, where a marker block is placed on the sternum upper abdomen, and based on that signal we can trigger the beam in deep inspiration breath hold. Now, over the years, we've built up a lot of experience with this technique, and we start to realize some of the limitations of that surrogate system approach. One example is shown here, where a patient is using back arching to bring the marker block in the right position. Which is shown in the feedback system provided to the patient. But in this case, with the back arching, the block might be in the right position and you detect a correct breath hold. But what you see here on the right in this animation is that the chest wall and the breast are not in the right position in this particular case. So this triggered us to investigate surface scanning and SGRT. Since 2018, we moved to SGRT for deep inspiration breath hold, and where we use the entire breast directly as the triggering device using surface scanning. Yeah, we saw the added value because you directly use the information of the breast position. That's one thing, and also in terms of setup, we definitely saw an improvement compared to the tattoo-based setup that we used with RPM. It also meant that in some cases we had to modify the image guidance protocol. Our standard image guidance protocol was KV-KV imaging for breast, but as you can see here, the gantry blocks the view of the camera that gave best access to the left breast. So in this case we modified the image guidance protocol to an MV-KV approach with another gantry angle, so that the camera having the best view to the left breast would not be blocked. We started off using SGRT for deep inspiration breath hold in left breast, but then expanded SGRT towards other sites, as you see a list here. Also right-sided breast, gynecological, prostate, extremities, but also SBRT lung and intracranial SRS and SFRT. And let me show you a few results there. So the setup for lung SBRT, we also use SGRT, and you see that the events where a roll correction of larger than 1.5 degrees was required is substantially reduced using SGRT from over 30% to 12% of the setups, which is a nice improvement. Also in the delivery of hyperarc for brain irradiations, we use surface scanning. The hyperarc technique is a highly automated multiple arc technique for brain irradiations. On the left, based on the isodose lines, you can see the high conformality that can be achieved with this technique. These multiple non-coplanar arcs make it quite hard to use image guidance during delivery. That's why we use this approach. We use an open face mask. Cone beam CT imaging is used at the gantry at 0 in the beginning to verify the position of the patient. During delivery we don't use any X-ray imaging, but we rely completely on SGRT. So with each couch rotation for each non-coplanar arc, we verify the surface compared to the reference, and then continue. So also prior to applying the mask, we use SGRT to set up the patient properly. Then we apply the mask. During delivery, the AlignRT version 6.2 automatically selects the right angles. And with this approach, we can verify for each couch angle the position relative to a reference capture that is acquired right after acquiring the cone beam CT. And in this way, we have a highly efficient way of delivering these complex brain irradiations verified with SGRT. Let's move on to another type of linear accelerator, the closed bore O-ring system. So in this case, we can ask ourselves the question where to position the cameras so we get the best performance of the SGRT system. In a Varian Halcyon system, you obviously have a treatment isocenter inside the bore. But that's difficult to access by the RTTs, for example, to correct the setup of the patient. You also have a so-called setup isocenter, which is in this case about 60 centimeters in front of the treatment isocenter. So you have a laser system pointing at that isocenter. It's much easier to access the patient at that point. So this is a specific position to set up the patient. In this simulation study, we used ray tracing to look into the interference of the Halcyon gantry and the camera views. As you can see here, for a breast patient, we were able to, with all 3 cameras, acquire the surface at the level of the breast. But if you look at the arms, there's only one pod that can capture that part of the surface, and also the arms are visible or can be captured up to the level of the shoulder, but not much further. And that might be a little bit limited to position a patient, in this case a breast cancer patient, where we know that the position of the arms is very important. We also did a similar study with a patient inside the bore at the treatment ISO center. And there, with the 2 cameras on the side, the left and the right, you don't see anything. With the central pod, you can see something, but it's also fairly limited what you can see. And you might have to lower the camera to a height that is not very practical. You might bump into it. So certainly inside the gantry bore for the Halcyon, the visibility of these ceiling mounted systems is limited. The Halcyon workflow consists of 2 steps, and the first step is in front of the bore at the level of the setup ISO center, where we position the patient and using Align RT correct the position and the setup. And then a second step where we move the patient in the bore and at the same time apply the delta couch. That's the shift, the known shift between the setup ISO center and the treatment ISO center. For that we need 2 treatment plans, one clinical plan for treatment delivery and the other one for the setup with Align RT, where the setup ISO center, where the setup point of the patient is the same as the ISO center. It's a plan that cannot be used for treatment, but is required to do the setup with Align RT in front of the bore. The Halcyon has a streamlined IGRT workflow, but it's really important, and that's why we see this as a very nice combination of surface scanning in front of the bore and then the workflow of Halcyon inside the bore. That combination is optimal in our opinion. So from the previous studies, we concluded that the visibility of the patient surface inside the treatment bore for an O-ring system was fairly limited. So that's why we got interested in developing an intra-bore surface scanning system. And that's what this paper reports on. So based on Microsoft Kinect technology, 1 or even a 2-camera setup, such a intra-bore surface scanning system was developed and was in this case validated with 3D printed phantoms. The data you acquire with these cameras is interesting. As you can see here, you can during a breast VMAT treatment, we captured a baseline drift. You see the breathing motion, of course, but also a baseline drift. You can also quantify the couch shift applied after COMIM-CT image guidance. The Halcyon is very fast in acquiring COMIM-CTs and in delivery of VMAT. So that's why we saw a lot of potential in using that device for deep inspiration breath hold. So we started up a study using the DIN-R spirometer. That's a commercial device for breathing motion capturing inside the bore. And during these deep inspiration breath hold breast cancer treatments, the surface data was acquired with our home-built surface scanning system. As you can see here, it was a dual camera system that we mounted at the back of the bore to capture the data inside the bore. The results of this study were quite positive. So the Halcyon seemed to be proved to be a very good platform for deep inspiration breath hold, a very efficient delivery, So mean treatment time of 7 minutes and 36 seconds, including COMIUCT and 3 VMAT arcs. And also important to mention that 92% of these fractions were performed in 4 breath holds, so that means 1 breath hold for each component. And that's the more breath holds you need, the more tired the patient gets and the more difficult it becomes. So this is really efficient in the amount of breath holds that you need. And also this study was performed in a population aged over 70. This gives you an idea of the quality of the signal that we acquired with this surface scanner, intra-bore surface scanner. So you see the baseline drift that happened here, and the breathing motion, but also baseline drift and shift. You see there the correction after COMIUCT that is applied. You also see in this case the spirometer. Well, there's no airflow during the breath hold, so they have a flat line, but you don't have any information on the position of the patient, while if you look at the signal from the intra-bore surface scanning, you see that indeed something happens during that breath hold. And also you can monitor the amplitude of the breath hold for the subsequent breath holds. In these results, well, you see what kind of signals you can capture. So on top you see an excellent fraction, only requiring 4 breath holds to complete the entire deep inspiration breath hold treatment, including COMIUCT and 3 VMAT arcs. Second one shows some more difficulties, requiring some more breath holds to complete the entire treatment. I see 8 in total. But after these difficulties, the patient was trained, re-coached, and then you see an improvement going back to the really efficient 4 breath holds. So beside proving that Halcyon is a very good platform for deep inspiration breath hold, this study also showed that intra-bore surface scanning really has an added value in monitoring the patient during treatment, and there's potential to also drive the deep inspiration breath hold triggering with that signal. So we're happy to see that recently this Align in-bore system was introduced by Vision RT, and we're looking forward to see how this system can be used for deep inspiration breath hold in Halcyon. Fairly recent, we started proton therapy in Leuven, and we also have a surface scanning device installed on our IBA Proteus One system. So let's have a look at how we intend to use SGRT in proton therapy. In July 2020, we started treating patients. Today, we have treated already 10 patients since then. We treat the indications that are reimbursed in Belgium, so the so-called standard indications are reimbursed in Belgium. You see a list of some of these pretty rare tumors mainly focusing in the first stage on intracranial treatments, but also moving forward to craniospinal treatments. This is a setup of Align RT on our Proteus One system. So 1 camera inside the bore and 2 cameras outside the bore. It's the first installation of an Align RT system on an IBA Proteus One. It's a compact gantry, which means it doesn't rotate the full 360 degrees. As for some treatments with 2 lateral beams, for example, you need in between these fields a couch kick of 180 degrees. It has a small field size, 20 by 24, so that means for example, craniospinal with large target volumes, you need quite a lot of isocenters to cover that volume. In proton therapy routine today, a lot of centers do X-ray imaging after each couch movement to verify the couch position. So there's definitely some potential here for SGRT. For patient setup, for patient monitoring, verification of couch movements, breathing related triggering. Yet it's another geometry for the camera system. So we definitely have to look at the performance of this system. It's an asymmetric setup, so one camera inside the bore, two outside the bore. And in proton therapy, the interference with the movable nozzle and the range shifter should definitely be investigated. Similar to what we did for Halcyon, we also came up with this geometrical model of the Proteus 1 and the nozzle of the system, and had a look at how much clearance, so how much distance was required for the camera system to be able to capture the surface. And we came to the conclusion that if you move this range shifter closer, you need at least 22 centimeters of clearance to be able to capture the surface and to do SGRT in this case. However, for the zero gantry angle, that's of course worst case. For other gantry angles, it might be less of an issue. The performance of the position measurement of, in this case, a phantom, we investigated by applying known shifts with the couch, with the robotic couch. And you see here an excellent agreement, sub-millimeter, sub-degree accuracy of the surface scanning system. In this medulloblastoma case, we used a line RT to set up the patient. It was a very small child of 2 years of age, and in this case we saw that using a line RT prior to applying the mask, we improved the position of the patient, position of the head inside the mask considerably, and less corrections were required afterwards based on imaging. We started in September also doing craniospinal irradiations with proton therapy. It's a typical case where you can spare a lot of critical organs for these patients compared to VMAT or IMRT CSI techniques. And with this compact gantry, we need many isocenters to cover the entire volume from cranium to the entire spinal canal. And here as well, we're investigating how a line RT can help us in improving efficiency of this treatment and quality by, for each isocenter, defining a region of interest to position the patient and also monitor the patient during treatment. With this, I would like to conclude my overview of how we use SGRT in UZ Leuven. The future goals are definitely to use this technology for even more patients to improve quality and efficiency of the treatment. We'll also keep investigating how surface scanning technology can be better integrated in treatment units. I would like to thank you all and take care.